Van't Hoff Factor. So whenever a solute is undergoing association or dissociation in solution, molar mass becomes abnormal. Molar mass is not as expected. Is abnormal molar masses comes into picture. For example, if we have acetic acid in a non-polar medium, so in non-polar medium, acetic acid exists as dimer. So its molar mass comes out to be more than its normal molar mass, because and it depends upon the association, degree of association. Okay, same if NaCl is dissolved in water, it dissociates into Na plus and Cl negative, and therefore its molar mass comes out to be less. Its observed molar mass comes out to be less than the actual molar mass of NaCl. So whenever association or dissociation takes place, whenever association or dissociation takes place, then Van't Hoff factor comes into picture. It is denoted by I, and it is equal to observed colligative property divided by calculated colligative property, or experimental colligative property divided by theoretical colligative property, or abnormal colligative property over normal colligative property. Or in terms of molar mass, it is just inverse, that is normal molar mass divided by abnormal molar mass. Or in terms of number of particles, it is defined as number of particles after association or dissociation divided by number of particles irrespective of its nature. They may be ions, they may be associated molecule, like that. Okay, so number of particles before association or dissociation, right? Number of particles after association or dissociation divided by number of particles before association or dissociation. Okay, so now let's calculate Van't Hoff factor for dissociation. Let's say we have a molecule AN, it dissociates into Na. It dissociates into n number of particles. Okay, it dissociates into n number of particles. Okay, so now if alpha is degree of dissociation, and you know what is degree of dissociation, that out of 1 mole, alpha moles undergoing dissociation. That's what alpha means. So let's say initially we have 1 mole of AN, so it is 0 initially. Now at equilibrium, out of 1 mole, alpha moles undergoing dissociation. So if out of 1 alpha undergo dissociation, so that becomes n alpha, number of particles becomes n alpha. So number of particles after dissociation is equal to 1 minus alpha plus n alpha. That means it is equal to 1 plus n minus 1 alpha, right? Okay, I'm fantastic, beta, and hope you are doing well. So it is 1 plus n minus 1 alpha, or I can write here because and number of particles before association, before dissociation, sorry, that is only 1. So I comes out to be 1 plus n minus 1 alpha divided by 1. So it is I equal to 1 plus n minus 1 alpha. That implies n minus 1 alpha is equal to I minus 1. And see, this is value of I, that is 1 plus n minus 1 alpha, and alpha is equal to I minus 1 over n minus 1. So these are the two values that you should keep in mind for dissociation. Okay, first is I is equal to 1 plus n minus 1 alpha, and second is I alpha equal to I minus 1 over n minus 1. Right? Got it? Now association. These two equations for dissociation. Now for association. Let's say n particles associate together to give an. So initially, again, let's start with 1 mole is 0. So at equilibrium, alpha is now degree of association. In the previous case, alpha is taken as degree of dissociation. Now alpha is taken as degree of association. So out of 1 alpha particles associate. So see, when n particle associate, we get 1. Okay, after association we get 1. If 1 particle associate, we get 1 by n, and if alpha associate, we get alpha by 1 after association. So alpha undergo association, so we get alpha by n after association. So number of particles after association, number of particles after association is equal to 1 minus alpha plus alpha by n, means 1 plus 1 by n minus 1 alpha, and number of particles before association is equal to 1. So in this way, now I is equal to 1 plus 1 by n minus 1 alpha divided by 1. So I comes out to be 1 plus 1 by n minus 1 alpha. So this is Van't Hoff factor, and degree of association I alpha equal to I minus 1 divided by 1 by n minus 1. Now, for 100% dissociation, 100% dissociation means alpha is equal to 100%, means alpha is equal to 1. So if alpha is equal to 1, I comes out to be 1 plus n minus 1 into 1. That implies it is equal to 1 plus n minus 1. So it is n. So I is equal to n only. That means number of particles we are getting after dissociation, that is the I, if 100% dissociation takes place. For example, NaCl, if it undergoes 100% dissociation, then what is I for it? Yes, tell me. What is I for NaCl if it undergoes 100% dissociation? Yes. If it undergoes 100% dissociation, what is the value of I? So let me tell you, NaCl. So if NaCl undergoes dissociation, it give Na plus and Cl negative. Means how many particles it will give? 2. So I is equal to 2 for NaCl. Now K2SO4. What is I for K2SO4 if it undergoes 100% dissociation? So if it undergoes 100% dissociation, you know, K2SO4 will give 2K plus and 1 SO4, 2 negative. So I is equal to 3 because 2K plus and 1 SO4, 2 negative. Total number of particles it will give are 3. Romit Prajapati, very good. It is 2 for NaCl, and for K2SO4 it is, for K2SO4 it is 3. Now if we have CaCl2, let us say, and it undergoes only 40% dissociation. Let's say it undergoes 40% dissociation. Then what is I? So see, CaCl2, it will give Ca2 plus and 2Cl negative. N is 3. But now we have to apply the formula I equal to 1 plus n minus 1 alpha. Means it is 1 plus, what is n? N is 3 minus 1 into 40%. So it is equal to 1 plus 2 into 0.4. So it is 1 plus 0.8. So I is equal to 1.8. I is equal to 1.8. Right? Very good. Good, beta. So now let's go for association. Now for 100% association, again alpha is 100%, means alpha is equal to 1. So I is equal to 1 plus 1 by n minus 1. Alpha is 1 only. So I is equal to 1 by n. I is equal to 1 by n. Now, dimerization, tetramerization, hexamerization, anything, polymerization, any polymerization. So in dimerization, two particles associate to give one particle, that is called dimerization. If 100% dimerization, 100% tetramerization, 100% hexamerization, 100% polymerization takes place, let's say, so what is I for it? It is 1 by n. What is n? 2. So in dimerization, I is equal to 1 by 2. For tetramerization, I is equal to 1 by 4. For hexamerization, I is equal to 1 by 6. And for polymerization, I is equal to 1 by n. So that's the theoretical part of association, dissociation, Van't Hoff factor, abnormal molar mass. So yeah, keep in mind that whenever association takes place, in association, molar mass will increase and colligative property will decrease. Why? Because number of particles after association are less. Okay. And for dissociation, for dissociation, number of particles will increase, molar mass will decrease, and colligative property will increase.